Okay, here we go. IMFs, intermolecular forces. Okay, intermolecular forces. So whenever I talk about IMFs, that's what I'm talking about, intermolecular forces. Using those words, what do you think that means? Intermolecular forces. Okay, how the molecules interact with each other. That's good. Okay, so up to this point, we've talked about covalent, molecular, ionic, some alloys. The ionic, covalent, polar covalent, metallic, this is how the molecules are, how we made molecules. Okay, now we're talking about how this molecule interacts with this molecule. Okay, intermolecular forces. Okay, and there are 3 of them that we're going to be worried about. Okay, the first one we're going to talk about is hydrogen bonding. Or yeah, they call it bonding. People, bonding. We've got some scientists right now that are fighting for this to actually be called a bond because it's stronger than the others. It only works if you have nitrogen, oxygen, or fluorine directly connected to a hydrogen. So I call it NOF, directly connected to a hydrogen. And if you look at the periodic table, N, O, and F are right next to each other on that second row. So nitrogen, oxygen, and fluorine, it has to be directly connected to a hydrogen. So I have to have a nitrogen directly connected to a hydrogen, or an oxygen directly connected to a hydrogen, or a fluorine directly connected to a hydrogen. When I have that, then I can do what's called hydrogen bond. The one that you're probably the most familiar with is water. So if I do water, it looks like this for oxygen. We have a hydrogen that comes in here, and we have a hydrogen that comes in here. Okay? If I were to draw a bunch of these in a simple form, I'm going to use oxygen being red, I would look like this. Okay, and I would have 2 unshared pairs of electrons. And if I look at this a little bit closer, I can say, you know what? This side is slightly positive. So we use a small delta. I don't know if you're familiar, I'm going to do that in black, with a small delta. Most of you know delta being like this. This is a small delta. Okay? I have a slight positive. It doesn't mean a full positive because they're not ripped apart from each other like in ionic. But I have a slight positive on this side and I have a slight negative on this side. Well, that forces water to arrange in a certain pattern. So it arranges so this water is then attracted by another water that looks like this because it's attracted to its unshared pairs of electrons, which is attracted to another water like this, okay, and it keeps going. You know that water expands as it freezes. That's why, this is the reason why. Because of this hydrogen bonding, it has to arrange itself in a specific way. When it's liquid, they sort of flow over each other. And they get a little bit attracted, and that's why you have the meniscus and stuff going up. This is hydrogen bonding. They're attracted. So it's not really a bond, it's like a attraction, but not a full bond. Okay? But we call it hydrogen bonding. So that's the first one. The second one that we're going to talk about is dipole-dipole. Dipole-dipole. On this one, this can happen with any molecule. Okay? So say that I had sulfur this time in the center. And we're going to still do a bond, but this time we're going to bond with a chlorine and another chlorine. And this one's a little bit harder. I should have probably picked a different one. But chlorine is really close to fluorine on the periodic table, right? And we know that fluorine is the most electronegative. So chlorines will pull the negative to this side a little bit. It'll be like a tug of war, but they get a little bit more of the electron. So that makes, let me do it in red so you can see it. That makes this side a little bit electropositive because the electrons are being pulled away from it. This is known as a dipole. When I can set it up and I have a slightly positive side and a slightly negative side, it's a dipole. And because of the dipoles, it's just like positive attracts negative. It'll set up so it arranges that way. I can also do a simple, a more simple dipole when I do like, say, pH3. So here's an H, here's an H, here's an H, and we have an unshared pair of electrons. What shape was this? Do you guys remember? The unshared pair of electrons did what to the shape? It pulled it out. So we had, we had what I called the ghost up here, and that pulls that out of the plane, so we have a trigonal pyramidal. So because it's a trigonal pyramidal, it sort of looks like this, with that up there. So I actually end up having a slightly positive side and a slightly negative side. Okay? And because I can do that, then I have a dipole-dipole. And the positive side will be attracted to the negative side, and the negative side will be attracted to the positive side, and they'll just arrange that way. So that's known as a dipole-dipole. So they have somewhat of an attraction for each other. Okay? Any questions with dipole-dipole? You understand the difference between that and hydrogen bonding? Yes?
Do they not attract like hydrogen bonds?
I was waiting for this. Hydrogen bonds have a little bit more attraction, but they also have dipole-dipole. So I can have all three of these IMFs that we're going to talk about.
So hydrogen bond doesn't have both dipole-dipole and hydrogen bonding and whatever the third.
Right, right. So hydrogen bonding has more of an attraction than just dipole-dipole.
Now, will dipole-dipole also have the third one? Because it doesn't
Right, right. So usually dipole-dipole will have two. So hydrogen will usually have three, dipole-dipole will have two, and the last one will just be itself. Okay? Good questions. Anything else? Okay, so on the last one, this is the one that most people go, okay, this is London dispersion forces. Or what we call LDFs. Because that gets really long, and you know scientists like to do shortcuts. Okay, so LDFs are basically any other intermolecular bond. So basically, it's just because you got put in this room, you have an LDF with everybody else in this room. Okay, you have a bond. It might not be a one-on-one bond, but you sort of know who everybody is in this class, kind of thing. Does that make sense? When you move up to the dipole-dipole, you sort of have somewhat of an attraction to somebody else in this class. Does that make sense? When you go to a hydrogen bond, that would be like, oh, we're dating. Okay, it's a more strong bond than just a friend bond. Does that make sense? Try to make it into that form for you. So this one right here, this could be something like just chlorine to chlorine. Okay, what kind of bond was that? What kind of bond do I have here? A linear is a shape. What kind of bond, though? Polar, covalent, covalent, ionic, metallic. What kind of bond? Covalent. They're both the same, so it's covalent. What is really important here is sometimes LDFs can overtake hydrogen bonds in strength. And the way they can do that is if we have something like this going on. What's different here? I have a little teeny molecule bonding to a really big molecule. Okay? And what can happen is all these electrons are on this really big molecule, sometimes are on one side of the molecule compared to the other, because remember they orbit, right? And so sometimes they get shifted off to one side, and that causes a dipole effect, which makes it a stronger bond. Okay? Just know that LDFs for the most part are weak unless we have an itty bitty to a large molecule. Okay? So these are the three forces or three bonds that we call intermolecular forces or IMFs. All right? How we doing? Dipole-dipole is if I can, when I draw the molecule, if I can split the molecule and get a positive, slightly positive side and a slightly negative side. So here on this one, when I split it, I'm basically splitting it here. Yep, remember, it sort of builds up. So if I have an LDF and I go to a dipole-dipole, I still have a dipole-dipole and an LDF. If I go to a hydrogen bonding, I still have hydrogen bonding, dipole-dipole, and LDF. All going on at the same time. One more time, sorry. Okay. I saw a couple other hands go up.
Yeah, I was just wondering, do we always split it like wherever the line bonds are?
Yeah, you usually want to split it so it's like separated. So let's look at a couple more. Let's bring this down and get some more paper here. So I'm going to just give you some examples and let's see if we can classify them, okay? So say that I had a nitrogen, which would look like this, and I combine it with a fluorine. So I'm going to combine it with a fluorine. And if we did dots, this is how I would do it with dots. If we do it line, makes it real easy. Okay, what do I need to, yes? One of them will be dipole-dipole, yep. How did you get that? The unshared pair of electrons, which I call ghosts, but you got to remember is unshared pairs of electrons. Okay, what does it do? It pulls it out of the plane. Okay, so then I get what looks like that, right? Sorry, those two dots went together. So because that unshared pair of electrons pulled this out of the plane, I now can have a dipole-dipole. What if it didn't pull it out of the plane? It would just be an LDF. So this would be a dipole-dipole. Sorry, there's no shortcut for dipole-dipole. And a what? LDF. Okay, so let's take one that doesn't have an unshared pair of electrons. Let's take boron trichloride. So we have boron, a chlorine, and a chlorine. Remember, boron and aluminum sometimes do weird things here. Okay, what shape? Do you guys remember? Trigonal planar, good. Now that means that I'm not going to be able to separate that B out, right? It's going to be surrounded by C's. This would just be an LDF because I can't, even though the bonds themselves, this one is more positive and this is more negative, and this is more positive and this is more negative, and this is more positive and this is more negative. The positive's in the center, but the negatives are all around it, so I can't separate them out. Okay, so that is LDF. Okay, let's do another one. What if we replaced nitrogen with hydrogens instead of doing the chlorine or fluorine that we did up above? Okay, it will be dipole-dipole because we know that from up above, right? Because of our unshared pair of electrons pulling it out. It's also a what? How do you know it's a hydrogen bond? Good. So just remember NOF, if it's nitrogen, oxygen, or fluorine directly connected to a hydrogen, NOF, it's going to be a hydrogen bond. Okay, what else? It's an LDF also, yes. No, It only can be a hydrogen bond if it's hydrogen with nitrogen, oxygen, or fluorine. So when we did up here, let me bring this back up. When we did hydrogen to a chlorine, we had an LDF, but because it was a little to a small, it's a very strong LDF. Okay?
That wouldn't be affected by would it?
If we look at the electronegativity on that, chlorine is closer to what hydrogen is. Hydrogen's a 2.2, and remember fluorine is a 4.0, and if you look at that paper, I can't remember exactly what chlorine is, but I'm thinking it's close to a 2.9 or 3.1, something like that, so the difference is not great. Right. Okay? All right, so is everybody okay with what we're doing? You understand how to figure it out? Important, important, important. We good? Okay, so let's bring up on the next page then your molecular geometry. Pogil. Okay. Let me see if I can bring this up a little better. Okay, we're going to get into our groups with this, but I want to just do this first part with you. We're going to split into our groups. I'm going to have red. You're going to be in charge of keeping track of the time and keeping people moving on this. Green, you are going to be reading the instruction areas. Blue, you're going to be in charge of reading any diagrams or pointing out important things in the diagrams. And what's the other color? Orange, you are reading questions. Okay? All right, so as we look at this, why? Why are we doing this? We've done a lot of VSEPR. We've done a lot of spatial things. We're actually going to play with models next time. So we're going to actually build these molecules and see how they go together. Okay? When you draw a loose structure for a molecule on paper, you are making a two-dimensional representation of a three-dimensional thing. Okay? In reality, molecules are not flat. Okay? They are three-dimensional. The true shape is important because it determines many physical and chemical properties. It determines the intermolecular forces, the IMFs, okay, for a substance. You'll learn how to predict molecular shapes, and we've been doing this a lot. But I wanted one more push before we actually play with the models next time, okay? And then we're going to be heading into stoichiometry, which is what your quiz was about today, with going from grams to moles and moles to grams. We're going to be adding on to that. Okay, so your time today for the rest of the period, so watch the clock. You want to get this done. You want to get it turned in. You're welcome to use the goodies to help you keep up, whatever, okay? Going to face backwards, 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 and backwards, 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 okay? Got it? So first row and third row, you turn around and face the second and the fourth row. Okay, let's begin. Yes?